All right, this is going to be the first of three parts that cover Chapter 16 for AP Statistics, which is about sampling distributions. And this lesson will be fairly close to the published notes. There might be some slight variations because we alter this a little bit from year to year. And I had to make some allowances this year because there's different things we can do as far as activities because we don't have the same amount of time with students in person. But all the same ideas are in here. And this particular lesson and the part two lesson tomorrow is going to be highly dependent upon an app that I developed that's on my website at mrfelling.com. So if you have a phone available with the ability to browse to a page and do that separate from the computer, that will help in understanding this stuff. All right, we're going to go ahead and get started here. So chapter 18 is about sampling distributions. And I'm going to add a little intro here that takes the place of some stuff that we're able to do when we're in person. This is a good summary for every year, though. In first semester, we've seen that we're often working with a sample that's taken from a population. And first semester focused on different ways to analyze the sample that we took, right? In the second semester of AP Statistics, we're now going to focus more on what can that sample tell us about the population that it was sampled from? In other words, what can we infer about the population from analyzing the sample? So that particular type of statistics is known as inferential statistics because we're inferring things from the sample to the population. What we studied in first semester was really called analytical statistics. So it's just what can you do to analyze the data that you have available. All right. So whenever we use a sample to analyze a population, we should keep in mind that things are happening at three different levels. So this is my way of understanding it, and I think it's a really good way. I refer to this, and it just solves a lot of problems to think in terms of these three levels. So I'm going to mention this a lot throughout the rest of the course. The three levels we're working at in inferential statistics are, number one, the top level is the population itself. Number two is the sample that we took from that population. And number three is what we call the sampling distribution model. So I'll explain all these in more detail. The population itself is the group that we're trying to study and that we want to be able to generalize our results to, or we want our results to apply to that. So anytime we're measuring some numerical value about that, since it's a population, that would be called a parameter. And we would typically use Greek letters like mu for the mean, sigma for the standard deviation, right? So that's what we're trying to study, right? But typically we can't take a census of the entire population. We have to use a sample. So the second level that we work at is the sample itself. So when we take a sample of size n is our letter for the sample size from that population, then if we compute something from an analysis like a numerical value, that's called a statistic, right? Parameters go with populations, statistics go with samples. And we have different letters, typically based on regular letters instead of Greek letters. So the mean would be R for the statistic from the sample, and that would be some sort of an estimate of the mu parameter for the population, the mean for the population. And the sample standard deviation would be called S, and that's an estimate of the population standard deviation sigma. Okay, so statistics are estimates from a sample of their corresponding population parameter value. All right. So, but the thing is whenever we take a sample, that's not going to be the entire population. So that's going to have some variation. Every time I take a different sample, I'm going to get a little bit different result, right? Every time you take a sample, you get a different result. When you analyze it, things like means, standard deviations, proportions, or any other statistic, that's going to vary from sample to sample, right? That's totally expected. And we call that variation natural sampling variation or random sampling variation. So what the sampling distribution model is it's a model that shows how we would expect the results of one of the statistics to vary from sample to sample. Most of the time we're talking about the measure of center, which is the mean. So, the population has a mean mu, and the sample has a mean x bar. And if we take a bunch of samples, they each have means, and the sampling distribution model shows me how those means vary from sample to sample. Okay, so mostly what we're going to be dealing with in chapter 18 is this level, the sampling distribution model. Okay, all right. So the neat thing about the sampling distribution model is then we can use that sampling distribution model to determine how unusual a particular sample statistic would be. And that helps us to determine if things are statistically significant, like if the difference from giving the drug is statistically significant. It's based on what happened in the sample compared to how much variation we expect there to be in that thing from the samples. All right. All right, so we're going to examine how sampling distributions work, and to help see that, I've got a number of applications that are written online for you to use. So if you can use your phone to browse with your web browser to www.mrfelling or just mrfelling.com, and then /SA1 stands for Statistics Activity 1, SA1. Okay, now when you do that, you should get a screen that looks like this. So I'm going to show you on my web browser here on the computer. So it allows me to specify a shape for the population level and a sample size, and then to take a sample. Okay, so here's what I'll do. With that showing, let's leave this at normal like this, but let's set the sample size to 9. So just click in there and then type in a 9, and then click the sample button. And what will happen is it'll run. It takes a while to run this, and it'll give you a display like this. Let me see if I can make it connect up. I'm going to leave it kind of big. All right, so what this is the 3 levels that I just talked about: the population, the sample, and the sampling distribution model. Okay, so up here in gray, we have the population, and we specified that this was a normal population. This activity is hard-coded to set the population mean to 60, so this is centered at, there's a normal bell curve centered at 60, and the standard deviation is 20. That means 20 on either side of this, okay? All right, and then we took a sample of 9 randomly out of this. There's a very large sample here. I think I have it coded to be 400 or 1,000 different pieces of data in here. So we're taking a sample of 9 of those pieces of data. And you can kind of see them if you look closely. There's little blue dots that are randomly. So we took, of all the hundreds of dots in here, we took 9 of them, okay? And so down here at the sample level, it shows the sample of 9. It's hard to see there, but there's 9 dots, okay? And that means that the sample itself has a mean and a standard deviation. So if I were to plug those values in this numerical value into a calculator and do one variable statistics, the average in the sample is 49.6 and the standard deviation is 13.5, okay? And so that means these statistics, like this sample mean of 49.6, is some sort of estimate of the real mean for the population, which is 60. But I expect this to vary, right? Because this was a random bunch of 9. Now, when you did this on your phone, you probably got a completely different sample, because when you ran this, it's truly random. So you got a different random group of 9, okay? All right, and then this particular mean, we're going to keep track of where the middle is of the sample, the mean. Then there's a little red dot down here in the sampling distribution model. I've done one trial, I've taken one sample, and the mean happened to be right here at 49.6. Okay, so if you press the sample button again, what'll happen is you got the same population, but now I randomly take a different sample of 9. This time I got a more spread out sample. And this time my mean in the sample was 60.8 and my standard deviation was 29.6, right? Yours is different still. And that means that now I've got another dot down here in my sampling distribution. This red dot here is the mean from the second time I took the sample. And if you took, every time you press sample, you're going to take another sample. It's going to have its own mean, and it's going to add another red dot on here. So you can press that a few more times just to convince yourself of what's going on here. Okay. So what we really want to do is we want to take a whole bunch of samples. Basically, the sampling distribution model down here, it's supposed to be the picture of every possible sample that you could take of sample size n. Okay. And if I were to do that, let me try to do this. I've got another button here that says sample 400 times. That means take 400 separate samples of 9 each time with replacement. Okay, so if I press that button, it's going to add 400 red dots on here. And I'm going to see where all those averages, each one of these red dots is a different mean of a different sample. And it makes sense that they kind of all center around the real population mean. If the actual average in the population is 60, it makes sense that these should all be coalescing around 60. But I want you to notice something here. right? The amount of variation from sampled of the means is lower. The standard deviation down here is only 6.4, but the standard deviation of the individual values in the population is much higher at 20. So think about that for a second and ask yourself, okay, why is that happening, right? Let me go back to the notes for a second here, right? We've run through this examples, and now we've got our a sample of this, right? The standard, the most of the sample means are close to the mean, right? And the standard deviation is smaller. So first of all, this standard deviation, this distribution down here at the sampling model, it itself is a distribution, right? It's actually called the sampling distribution model of sample means, or the sampling distribution of sample means, because every piece of data in here is a mean of a sample. Okay, it's a little X bar. All right, so since that has a distribution, this shape here, this bell curve down here has a mean and a standard deviation. So the symbol for that is the mean of it is called the mean of the means, so mu of x. The reason we call it mu is because technically this is supposed to be of all possible samples of size n, so it's a population in itself, but it's the mean of a population of means. So it's mu sub x bar, the mean of those sample means. And this standard deviation here, so that's the standard deviation here is the standard deviation of the means. So this is the symbol we use for the third level, the mean and standard deviation of the sampling distribution of the means. Okay, so here's what I want you to think about, right? The standard deviation in the data was 20, but the standard deviation down here is much smaller. When I ran this before, I got 7.1. When I'm running it now, I got 6.4. So think about this. Why is that true? Why is the standard deviation when I average 9 things at a time less variable than when I take individual things? Okay, and there's a spot in your required packet for you to write down your thoughts on the first page of your chapter 18 required practice packet. So write down what you think. Why is it that this is true? Okay, I'm going to tell you what I would say. The problem with this is, right, if I take things one at a time from here, then I could get something be way out here at the end, way out here at this end, or anywhere in between. But if I take 9 things and then I take the average, the only way I would get a mean that's way out here is if all 9 of my points were in that region, right? If I had even one point that was over here, it would drag the mean down there, right? So that's why it's just so unlikely when we take 9 things at a time and take the average to get an average out in this region. And that's why all of the averages end up kind of staying in this region and why the standard deviation is lower. So I would write some words to that effect. For a sample of 9 to have a really high or low mean, all of the samples would need to be high or low. This is very unlikely, so the means end up closer to the middle, and therefore there's less variation in the means than there is in the original data. Okay? Okay, let's investigate that a little further because there's actually a formula for figuring out the connection between these two things, right? So I'm going to ask you to do this for yourself, and then I'll show you how to do this. You can reset this by just clicking reset. We're going to leave this at normal, but we're going to change the sample size and see what happens. So if when I did 9, let me do this over again. When I did 9, I'm going to jump right down to sample 200 times. Okay, so I can get the shape. And then I'm really after this number down here. I got 6.4 here when the original population standard deviation was 20. So I'm comparing the standard deviation of the sampling distribution of means to the standard deviation up here. So I got 6.4 here with 20. So on my sheet, and there's a place for you to do this in your required practice packet, right? I got that when n was 9, my population standard deviation was 20, but my standard deviation down here for the means was only 6.4. Okay. And then what you can do is you can reset and then set these other suggested values. So it says, let's try setting n equal 1. So we're just going to sample 1 at a time. So if I change this to 1, and then I take a sample, that just takes not 9, but just 1. And so that means the average is just the value itself. If I sample that 400 times, do that 400 trials of that, then my standard deviation is 19.5, right? So it's much higher. And that's because there's less averaging going on. We're really not averaging at all. So actually, this looks like kind of an approximation of the original population, right? All right, so when I had a sample size of 1, my population standard deviation is programmed in here to be 20, but I got 19.5 here. Okay, so what I'd like you to do is pause the video and then try this for n equals 4 and n equals 16 and write down what your values are here. These will always be 20. And then you can unpause the video and we'll talk about the result. Okay, I'm going to do this as well. If I run this with 4 as the sample size, so I'll run this with 4 as the sample size, and then I'll take a sample of 400 times here. Then I got 10.1. So when I ran 4, I got 10.1. And then if I do 16, let's try 16. I'll take a sample there, and then I'll take 400 of them so I can see what the sampling distribution model looks like. I got 5.1. All right. So let me just kind of round these numbers a little bit. This number is about 20. This number is about 10. This number is about 6. And this number is about 5. All right. So here's the next thing I want you to do. You take your numbers and round them. Can you see any connection between these two? Like if you wanted to make a formula that said X, you had sigma and you had sigma X bar, how would you make a formula that connects those two things? Think about that for a second. Pause the video, think about it, see if you can figure out what's going on here. Okay. And then I will do the same thing. Okay, so when I think about this, it looks to me like if I were to take, let's do this. Let me just see if one is maybe, I don't see that you could add one thing to another, like 20 plus 0 is 20, 10 plus 10 is 20, 6 plus 14 is 20. It doesn't seem like there's anything going on there. Maybe I could try taking one divided by another, like 20 divided by 20 is 1, and 20 divided by 10 is 2, and 20 divided by 6, that's not so great. What is that? 20 divided by 6, that's 3.3, and 20 divided by 5 is 4. 1, 2, almost 3, 4. Yeah, maybe we're onto something there. Yeah, now that I look at this, though, look at this. This 4 is just the square root of this 16. And this 2 is just the square root of that 4. And 1 is the square root of 1. And 3.3, it's pretty close to the square root of 9. So it almost looks like this. It almost looks like if you take the sigma value and you divide it by the sigma x bar value, you're going to get something that's the square root of n, right? Does that make sense? Yeah. Or if I wanted to solve that for this, what I could do is multiply both sides by this and get that sigma times sigma x bar is the square root of n, and therefore sigma x would be, let's see, that's not right. Can we get that right? So this part's right. Sigma over sigma x seems to be the square root of n. So if I multiplied, I would have sigma is equal to the square root of n times sigma x. And then if I divided both sides by the square root of n, I would get sigma x bar is equal to sigma over the square root of n. And in fact, that is the formula. You can actually prove this. And if you're interested, send me an email. I can send you a proof of this, of why this is exactly that the standard deviation down here is the standard deviation up here divided by the square root of the sample size, right? So not only is it less variable, but it's less variable in a very specific way, right? The mean always tends to be really close to the mean, but the standard deviation down here at the sampling distribution level is always this standard deviation divided by the square root of whatever you made the sample size, okay? All right, so what we have here is anytime for any data set, and it doesn't actually have to be normal like this, the mean of the sampling distribution, the mean of the means, will always align itself with whatever the population value is. But the standard deviation of the means will always be the population standard deviation divided by the square root of n. Okay. Now, what's really weird about that is that that works even when we don't have a normal distribution. Okay. So what we're going to do is look at other shapes. Okay. Let's do this. Let's click reset, and you can do this with me. Let's pick a different shape, like skewed. Okay. And I'm going to go to sample size 1 initially. Okay. If I click sample here, then that means my population is skewed. I made it skewed right like this. So most of the stuff here and slowly moving off to the right. If I took a sample of 400 of those things like this, I would get something that has more stuff on the left and less and less. It's kind of making a copy of the population. So very much not normal looking, right? And the standard deviation is, kind of in the same area, 20, 28, okay? But what happens if I increase the sample size? Let's increase it to 4. And then I'll run 400 trials so we can see something approximating the sampling distribution. So what's happening is the sample size goes up to 4, the standard deviation is getting smaller, right? But notice what else is happening. This is looking less skewed, right? And if I were to go up to 9, it's going to be even narrower. And it's going to start looking not at all skewed. In fact, it's starting to look like a normal distribution, right? And if I go all the way up to 25, and I take a whole bunch of trials, it looks very much like a normal curve, just as much as the normal shape did. So even if you start with a population that isn't normal, the shape of the sampling distribution is normal as long as your sample size is high enough. That turns out to be really, really important because we're going to want to use this level to calculate probabilities, how unlikely something is. And so it's nice that even if the population isn't normal, this number down here, this population down here is normally shaped as long as certain conditions are met. So let's jump up to the craziest case of all. You could also look at a normal case if you want. Let me go back to 1 for a second. Okay. Right. So this is a uniform distribution, meaning that everything is equally likely. And if you go through that, what you're going to find is as the sample size goes up, this gets more and more normal looking. Well, let's take the craziest case of all, which would be bimodal. I programmed a bimodal in here where the population had some very low numbers and some very high numbers and nothing at all in between. So if you take a sample one at a time, look at what happens, right? This time I got a sample that happened to be in the upper part, and so my mean was way up here. If I take a sample again, okay, this time I happen to get a sample that's way in the low value, right? And if I take a sample again, it's gonna either be high or low. In fact, if I were to take 400 samples, it would kind of replicate that. I'd have a bunch of low means and a bunch of high means and nothing in the middle. Okay, but what happens if I increase the sample size to just 2? You can go ahead and do this yourself if you want to follow along here. Right, so if I take 2 at a time in the sample, I could get 1 in the low and 1 in the high, which means the average would be in the middle. Or let me take another sample. This is another one where I had 1 in the low and 1 in the high, so the average was in the middle. Okay, this sample had both of the two things in the sample in the low space, so the mean was way down here. And of course, we could get the case where they're both in the upper. So if I do a whole bunch of samples, I'm going to get a bunch of them where they're in the middle here, where I had 1 in the low and 1 in the high, and a bunch of them where they were both in the low and a bunch where they were both in the high. And so this definitely does not look like the original distribution, but it doesn't really look like a normal curve yet either, right? But that's because I only took 2 at a time. What would happen if I took 4 at a time? Samples of 4. So let me go back and reset and do samples of 4. If you do 4 at a time, let me do 400. Then I have 1, 2, 3, 4, 5 possibilities. And you can see what's happening here is this is getting narrower and it's starting to fill in, right? Because the cases where we have some in each are more likely than ever than having this, because these ones down here means that all 4 of the dots had to have been in the low, or all 4 of the dots had to be in the high. Okay, now you can experiment with this. What this is going to ask you to do is to say, okay, let's try this. We can see that if the sample size goes up, these start to blend. So play around with this. You can pause the video and try like 12 or 9 or 16 or 25 or 50 and see what happens. Okay, so if you tried that, then what you probably found was this. As the sample size went up, the number of mounds got bigger and they squished in until finally at some point around the place where n is 16, and certainly by the time we got to n is 25, this shape has filled into a nice normal distribution. And the standard deviation got lower and lower and lower as the sample size got up. There's less variation. For the same reason, right? To get something out here, all 25 dots would have to be in the lower distribution, which is very unlikely, right? All right, so if you had to pick, there's a place for you to fill in your formula sheet. How far would the sample size have to be before you would say that's approximately normal? All right, so this result that no matter what the population shape is, if the sample size is large enough, the sampling distribution shape for the means will be approximately normal. That's known as the central limit theorem. And the reason why it's called that is not because it's about centers. It's because this idea is so central to all of statistics that it's right at the center of what we call inferential statistical analysis. So it's called the central limit theorem. It's sometimes abbreviated CLT because we refer to it a lot. It states this. This is the way our textbook states it anyway. If you were to put it in a sentence, it's the mean of a random sample has a sampling distribution whose shape can be approximated by a normal model. The larger the sample, the better the approximation will be. Now, exactly how large n has to be before you declare it to be approximately normal, that's kind of a gray area, and there's no real firm rule. Different textbooks have different numbers. Our textbook, in fact, uses 25. Once the sample size gets to 25 or higher, you can assume the shape is normal no matter how crazy the population looked. But the official AP statistics that was set when they redistributed the standards about a year and a half ago is 30. So the official rule for this class is now 30, regardless of what you see on websites or on the textbook. As long as the sample size is at least 30, then you can assume that the sampling distribution model shape is normal. Okay. All right. So that forms the foundation of inferential statistics, because now that I know that at this third level it's normal, it means I can postulate what's something called a null hypothesis. We're going to learn about this in chapter 20. I can postulate some value here. I can look at the value that occurred in my sample, and I can use a normal shape to figure out how likely this was, to determine whether this was unlikely. And that helps me make decisions about whether this is different from what I assumed. So this is the whole basis of how we're going to do analysis to determine if differences are statistically likely. All right, so just to summarize that, we've got these two formulas. When we're talking about a numerical variable, we have something that can be represented by numbers. Then the sampling distribution of the sample means is given by a shape which is approximately normal as long as the sample size is at least 30, okay? And the mean of that will be the mean of the population, and the standard deviation of that sampling distribution will be the population standard deviation divided by the square root of n, where n is the sample size, okay? But here's the interesting thing, right? This is required for all populations or any population. In other words, this guarantees that the shape will be normal no matter how crazy it is. If you have if you're sampling from a population shape that's closer to normal, then you don't have to have this rule. Let me show you that on the app so you can see what I mean. Right? When we have a crazy distribution like bimodal, if I only have a sample size of 4 and I take a whole bunch of trials, we wouldn't call this normal, right? So I would have to go up to around, say, 30. Let me use the book's answer or the official answer of 30. If I use a sample size of 30, then even though this population is totally crazy looking with a big gap in the middle, the sampling distribution is approximately normal because I used a sample size of 30, okay? But what if I'm sampling out of a population that is much closer to normal, like, say, for example, a uniform distribution, Okay, so if I had a uniform distribution and I just took samples one at a time, so a uniform distribution is one that's perfectly flat, everything's equally likely. Then if I just took a sample of one, that's not normal shaped. It's just spread out like a uniform distribution, right? But do I have to go all the way up to 30? Let's take a sample size of 4 and see what happens if I take a whole bunch of those samples. By 4, it's already starting to look like a normal distribution. So I don't have to necessarily go all the way out to 30 because this distribution looks, it's not that far away from a normal shape already. Right? Certainly by the time I get up to something like 9, let's say, then the sampling distribution, I think we could call this approximately normal. That's close enough to call normal, even with a sample size of only 9. And if we were to sample out of a population that we already know is normal or believe it's normal, then I could go all the way down to a sample size of only 1. And if I take that sample, then the sampling distribution model is going to be normal because it's sampling right out of a normal distribution, right? So the point is that this rule about having to have sample size at least 30, that's a guarantee no matter how crazy the population shape is. But if you're sampling from a population shape that's closer to normal, then n can be less than 30, sometimes substantially less than 30. If you're sampling out of a normal population, it can even be 1, sample size of 1. All right, so those are the concepts related to sampling distributions for sampling means, and that's where we're going to end this video. Tomorrow we'll talk about a case where we have non-numeric.